Okay, thank you, Joe. So we're gonna today we're gonna talk a little bit about the particle jets, what happens to them in the detector. So this is not very detector specific yet. We will come to this next week when we talk about how jet calibration is really done in Atlas. So let's see. Let me quickly recap the most important messages from yesterday. So clearly we have seen, hopefully, that the recursive recombination algorithms are strongly preferred in the sense that they deliver or give us physically meaningful jets that are infrared and collinear safe. The exclusive use of particles in the jets so that each particle contributes only to one jet, removes the need for split and merge. But of the three algorithms that are popular at LHC right now, only the KT and the Cambridge Eigen-KT have a meaningful cluster sequence. And we will come back to this when we talk about substructure. In general, the anti-KT configurations are preferred for precision analysis and event selection, just topology cuts and so forth, mainly because this particular algorithm does not have the so-called vacuum cleaner effect that the KT has, which means that in the recombination of the jet axis moves a lot at the beginning, and thus the KT have a really large catchment area, which means they are very kind of sensitive to pileup. The anti-KT is pretty stable in terms of directions right from the first recombination, and typically shows a small catchment area with much less sensitivity to pileup. We have seen that the seeded cone algorithms are not favorable. They're still used in low-level trigger applications, where it's really the only goal is to find energy flow in a cone, high energy flow in a cone, and trigger the event. There is a seedless cone algorithm that can be used to reconstruct heavy resonances. It's infrared safe and it's comparably fast. The ciscone implementation still needs a splitting fraction, which is theoretically, again, very little motivated. So those are the messages you probably want to take home from yesterday. So let's go and look at something new. So the first thing we can check is what is actually the composition of the jet in terms of stable particles. So the little plot you see here on the left is a specific version of Pythia. This is an old plot. I'm afraid it's Pythia 6, which has been tuned in terms of the production of flavor and the Parton shower with lab data. So in general, charged and neutral pions carry about 70% of the jet energy, where the neutrals, of course, show up as photons. So they are registered in this plot as photons. Charged and neutral kaons are the next big contributor with about 20%, and their neutrons and protons carry about 10%. This plot has been made for a center of mass energy of 14 TeV, if I remember correctly. I could not find the original paper yesterday, but I will try to add the source as soon as I can. And what is maybe not uninteresting to remember is that 60% of the jet energy is typically carried by charged particles. Because we're going to use track jets later on, and we have to remember that those are only give us a limited view on the jet, but have quite significant information on average on the energy flow, and the spatial resolution is very good for those jets. So each detector has a basically a cylindrical design laying on its long axis, with the beamline entering both ends of the detector. I like this particular figure, which is from our colleagues from CMS, which shows the expectations for what happens to particles emerging from the vertex, which is on the far left. So the magnetic field in the inner cavity, where the tracking detector is, will bend charged particles. This is here indicated by the red and green, and also somewhat the blue track. And depending on the nature of the particle, we expect that the photons and electrons will shower and will be stopped by the electromagnetic calorimeter, which is the first calorimeter right after the inner detector. This is typically true. These calorimeters are quite deep. They can completely absorb the energy of photons and electrons. Hadrons, on the other hand, penetrate much deeper, like this green track here. I know people like to show this as a typical hadron because the shower is in the hadronic calorimeter. But we should not forget that the electromagnetic calorimeters in ATLAS and CMS, especially in ATLAS, are quite dense for hadrons as well. So a lot of hadrons start their showering actually already in the electromagnetic calorimeter. The muon track, of course, muons don't really shower, and most of the muons don't really shower when passing through the matter of the detectors. So they are detected in the outer chambers where the muon detectors. They're not very important in the context of measuring jets, even though there are, as we saw yesterday, there's some conventions about what to do with muons and if they are found inside a jet. This is the math analysis needs for analysis goals. So the detector of choice for jet reconstruction is the calorimeter, because it basically has the ability to generate signals from charged and neutral particles. The calorimeters are designed to for precise energy measurement by fully absorbing the incoming particles and the energy. These particles will produce electromagnetic cascades if there are electrons, or hadronic cascades if there are any of the hadrons we saw. The signal that the calorimeter produces reflects the deposited energy of these particles. And we have to be really careful, because this is not the energy of the particle itself. It's only the energy that the particle deposits in the calorimeter, which is often less than the true particle energy, because calorimeters don't just hang in the air. They're surrounded by materials that absorb energies before the particle reach the calorimeter, including the inner detectors, the tracking detectors. And there's also effect of leakage. Some, especially hadrons, can leak out energy in the end of the behind the calorimeter. So these things disturb the energy measurement because we don't have full absorption. But it's always a good idea to make sure that whatever ends up in the calorimeter is well measured, and develop then strategies to recover the losses that are outside of the group. Muons, of course, we cannot measure the muon energy with a calorimeter very well. It basically, muons pass the whole device with just ionization losses, which you may remember the beta Bloch curve, which is very, very flat in terms of energy loss per centimeter in the region of interest. So if fast muons will just go through and don't generate any signal proportional to the energy. So we need the magnetic fields to measure the tracks in the spectrometer and in the inner detector. Calorimeters are notoriously bad when it comes to associating signals with collision vertices. They thus have a high sensitivity to pileup because we have very little judgment about which part of the calorimeter comes from pileup, meaning from interactions that happen at the same time as the one we're interested in, or which one comes from the one we're interested in. So having said that, it actually turns out that if you have a very nicely isolated photon, for example, in the ATLAS electromagnetic calorimeter, you can actually calculate back at least the small vertex has to be expected. This is very useful if you do like Higgs-2 photon-photon, where you don't really have many tracks to find the hard scalar vertex. Calorimeters are also limited in their capabilities to measure close-by energy flows, meaning separation of signals from particles that are very close together is not easy, calorimeter. this affects, or this puts some limitations on our ability to measure jet substructure with the calorimeter, but we will see in about 2 weeks that it still works quite well. The signals we get are still a good representation of the original energy flow. Of course, we have the tracking detectors, and those allow very precise reconstruction of tracks from charged particles emerging from either the hard scatter or the pileup vertices. Here we have excellent spatial resolution for the energy flow measurement. Unfortunately, they only reconstruct incomplete jets, if you want. 60% on average of the energy of the jet is carried by the tracks, but the fluctuations around it, this is a very broad distribution. And I remember to double check these numbers, I think it was like 20 or 30% on the RMS. So it's very broadly distributed. The good thing, on the other hand, is that whatever the track measures in terms of track activities, in terms of track momentum, can be very well matched to the calorimeter jet response. The ratio of these two is often a very good indicator, for example, to verify or validate calibration in the calorimeter. This we will come back to also when we talk about the jet calibration in Atlas. Clearly, the big advantage of the tracking system is it provides us with associations with the hard scatter or pileup vertices, so we can make judgments where particle flow actually comes from. And of course, you know that we combine both track and calorimeter signals to form energy flow objects that actually represent the best of both worlds. So we will come back to that when we talk about the inputs in the Atlas jet finding. Sorry, still don't know. So talking about calorimeters, we really have to introduce the concept of response and energy scales. And I know this is sometimes used in a funny way because it's not as natural as you may think. I remember I gave a presentation about this a long time ago in front of a few theorists, and they told me, what do you mean energy scale? Energy is energy. There's no particular scale. Of course, in the calorimeter, we see this differently because we can reconstruct whatever signal we get, assumption we have on the particle that generated the signal. And this we call an energy scale. The problem you probably know with both the CMS and Atlas calorimeters are they're so-called non-compensating calorimeters. That means a hadron entering the calorimeter at the same energy as an electron will deposit less energy, will generate a smaller signal in the calorimeter. And I have to correct myself that it will deposit the same energy, but it will create a smaller signal out of this energy deposit. So this is called a non-compensating calorimeter. And of course, this calorimeter, this has to be corrected. So the first thing we usually do is we build our calorimeters and we test them such that the response to electrons is linear. That means that there's a direct relation between the signal and the electron deposited energy. So this is this gives us a calibration constant in the truest sense of the word. And this constant is what we call the electromagnetic energy scale. So we take our reading indicated by the letter A here in green. This is our reading from the detector. We multiply it by a constant and we get a good estimate for the deposited energy on average if we have an electron in the calorimeter. Again, this deposited energy is not necessarily the incoming energy because the electron may have lost some energy up in front of the calorimeter, or there may be structures inside the calorimeter eating up some of its energy. But in general, the electromagnetic energy scale is a good reference. It's a basic energy scale we use in Atlas. And the direct proportionality is certainly an advantage in terms of simplicity of the calibration function. We can measure it in the test beam experiment. It's not as simple as people often think. The problem is that in the test beam, it's very hard to build a mock-up of the actual situation in the detector and a test beam. So you have different upstream materials, distributions especially, that make it very hard to measure this number directly. You have to use Monte Carlos. You have to simulate the response to carry it over to the detector. But this has been developed now. This is a standard procedure which started in the late 80s, and we pretty much understand now what we have to do. The electromagnetic energy scale is a good platform for data and simulation comparisons. So even if you don't have a fully calibrated hadron,
but in reality, it was just.
Sorry? Anyway, so it provides a good platform for data and simulation comparisons. Even if you talk about hadrons, this is fine. As long as the simulation has the hadronic shower model and the geometry of the detector correct, that describes the experimentally observed showers. So, but again, the electromagnetic energy is not the energy that gives you the true precise electron energy or photon energy. You often get very close, but there are other corrections that need to be applied. Of course, as I said, you can calculate hadronic signals as well. We thus, phrase the response of the calorimeter in terms of a given energy scale. We also have an hadronic energy scale, which is a scale which has some kind of calibration applied such that you get a better measure of the deposited energy by hadrons. And we have to highly non-linear, and we will talk a little bit about why that is in just a second. So this is a picture I like to show just to give you an idea why hadrons actually give you less signal. And this is purely an effect of the fact that hadronic showers develop following QCD rather than QED, which is the mechanics that creates electromagnetic showers. And that's much more predictable than the hadronic showers, actually. So if a hadron enters a nucleus, it will probably collide with, if its energy is high enough, it will collide with a nucleon, and this nucleon will get excited, or there will be an internuclear cascade which emits other hadrons. Here, for example, I show this pinkish is a pi naught, is a neutral pion, it decays immediately into 2 photons. Then there is a pi minus that travels quite a ways away to hit on another nucleus. And then there is a little pi plus that hits another nucleon in the nucleus and kicks it out of the nucleus. And then there's several levels of excitations and so forth possible. The important thing is that the hadronic cascade has several time scales. It's not just happening all at the same time. The internuclear cascade is at the QCD time scale, while the internuclear cascade has quite macroscopic time scales in the terms of nanoseconds. So hadronic showers take some time to make their way through the detector. And then there's a slow component on spallation and evaporation, which releases a lot of energy that we often cannot measure. And then there are, of course, all kinds of decays possible that are even may happen even later. The interesting feature is that we have intrinsic electromagnetic showers. That means the hadronic cascade has a part that looks like an electromagnetic shower, and that is a very important part for the response to hadrons. The whole process generates energies that are simply undetectable in most calorimeters. So we often have a non-compensating behavior as a consequence. So this, we can formalize this a little bit. So if you call pi the signal of a pion, you have a fraction of this as an electromagnetic cascade. This fraction is FEM, which reacts which gives you an electromagnetic signal. And then you have the 1 minus FEM, which gives you the hadronic signal. Not very important for practical application, but when you design a detector, you should watch these numbers. You should have an idea what your response will be. And from this, you can calculate some famous specifiers for calorimeter, like the E/pi ratio, the electron to pion signal ratio, and then the E/h ratio, the electron over hadron signal ratio, which is not the same as E/pi because it's only the part, it reflects only the part that is a pure hadron. So this is a study I did a long time ago, and it shows with the Giant version that probably is so historic I don't even remember the number, but it shows you what the different fractions of energy where they're invested in as function of the deposited energy. And you see FEM is on this log scale, energy log scale is basically rising linearly, and the invisible fraction, that is a fraction that cannot be turned into a signal at all, and the ionization fraction, which gives us a signal of the hadronic shower, are pretty much identical in this particular calorimeter. Actually, we studied this for Atlas, and in most Atlas calorimeters, it looks the same. This may be a model feature in Giant, but it's what we observe. So we try to parameterize the FEM, and the most famous parameterizations, there was one from Wickman's a long time ago, which is funny in that it's there's a rise with log E. It has to stop somewhere. It has to settle somewhere, and there was no prescription on when that would happen. So much more preferred these days is the Groom function, which is given down here. This is basically the description of the average evolution of the FEM as function of the incoming energy. You can judge yourself from the original paper. The plot there is from the original paper. You can make your own judgments whether this fits well or not. For now, we just live with it to try to understand a little bit about jet response. So this is all not very practical in terms of calibration. We basically never use this function directly, but it gives us an idea how the calibration function should look like as function, for example, of the jet PT, at least the shape. We have measured E/pi. It's a little tricky. I don't want to go into details here, but you see the result in the upper right plot. This is an old measurement with the H1 experiment with the calorimeter module that actually ended up in the detector later. So it's not just a calorimeter for academic studies. It was one that was actually used in physics. And you see the typical behavior of the E/pi rising with smaller energies. The values are also kind of typical and also very similar to what we see in Atlas. And you also should note that the E/h is significantly larger than the E/pi. It has been deducted from a fit of these curves with the assumption that the hadronic signal fraction, the hadronic signal is constant, is not energy dependent, which was motivated by this plot, where we see that the invisible and the ionization fraction are identical. So that means that once things go into an hadronic shower branch and don't have electromagnetic subshowers anymore, that basically half of that branch is visible in a signal and the other half is not. So you can calculate these numbers and you can fit the E/h or H/E, applying the Groom model. So we did this. This was slightly academic interest, but it was interesting to see how well this can fit and what the internal signal characteristics of this calorimeter really were. So now, if we move to jets, of course, as we have seen, this is a complex mixture of hadrons and photons, and it's obviously not a single particle response, but it has a feature that is interesting because in the jet we have already the part of the energy coming in as electromagnetic energy carried by photons. So if you just write down a very, very simple model, not getting too fancy about it, not worrying about fragmentation functions and whatnot, you can actually relate the jet response, which I call J here, to the electron response using the fraction of photons and the FEMs from Groome's formula. So it's a single particle approximation that yields for jets. So that is a simple model for jets. But why would we do this? I mean, it's clear this is not very realistic, but it gives us an idea of what the corrections will be and how well our calorimeter will actually work for jets if we plug in the right numbers. So many of the numbers you see in this formula, FEM, for example, and HOE have to be measured in the test beam if you want to get a realistic, somewhat average behavior of your calorimeter for jets. So this is in the early days of Atlas a lot, because we wanted to see how big the calibration factors are. You probably can imagine that the bigger the calibrations are, the less comfortable you are. Systematic errors, even the smallest percentage errors, turn into relatively large errors in the end if you have big calibration and correction factors. So we did simple plots like this, which shows the response ratio of jets and pions to the electron. You plug in a characteristic number, and you see that the jet response, as expected, is of course above the pion response. And we expect corrections to be conservative corrections about 1/60% to maybe whatever it needs. But actually, we later found in Atlas that in our lowest energy bins we need correction factors of 2, and the reason for that is what I want to talk about now. Because this single little model with just assuming the jet is like a single particle is of course not true. So if you look at a jet, and I just drew here a bunch of particles, the round ones are neutrals and the other ones have a charge, and I assign some energies to them, not very creative, just some numbers. So this is the result that comes out of the hadronization. These are the particles that are going in one jet, and let's assume the little dashed circle here catches these particles that go to the belong to the jet. There is a good amount of radiation and decay inside the detector volume. Actually, we saw some 2010 plots of hadronic decays inside the tracking, which I wish I could find. They're very impressive. So there is a randomization of the original particle content already going on. Even we used to call those coming out stable particles, but in the presence of material, of course, there can be Bremsstrahlung, there can be all kinds of decays can be triggered by the fact that there's an electric field or you're getting close to a nucleon. So there's some randomization going on just by the fact that there's a detector that has a finite amount of material. So now we turn on our magnetic field, and it's a magnetic field, so kind of gives the bends the tracks in azimuth, and you see the charge tracks kind of move a little further apart depending on their the sign of their charge, and the circle is already bigger. If you really want to catch everything, you have to do something. Now, this is of course not a problem if you use the charge tracks from the tracking detector, because that detector will reconstruct the track in the end at the original emissions direction, not at the one that is bent. But the bending is a true physical effect, so the particle will enter the calorimeter in the wrong place, if you want. So that is something to keep in mind. So the next step is, well, the bending has also another effect. If your particle is low energy or low transverse momentum, it can actually be bent away from the calorimeter. we used to call these curlers. So it basically spirals to the end caps of the detector, where it often cannot be seen because the energy is too low to reach a calorimeter. And it would actually, if it could be seen, it would not be nice if you want, because we usually don't reconstruct these spirals. We just reconstruct tracks that have a good momentum measurement and reach the detector. So we have some energy loss, or some loss of jet energy due to this lost particles in the magnetic field. And of course, other particles, charged and neutrals, have to go through whatever inactive material there is in front of the calorimeter, so they will shed off some energy as well. In this process, we will lose particles completely. The rule of thumb is that both calorimeter and tracking start seeing particles relatively well around 500 MeV PT. I think that is still the reconstruction threshold for tracks anyway in Atlas. We have no particular cut in the calorimeters. This is just an experience, if you want, because unfortunately the dead material in front of our detector is not it's not that little. It's quite a bit, and a lot of particles get stuck there. So let's assume we lost a few. So our circle becomes a little more oval. And now, when particles enter the calorimeter, they of course generate a cascade. So they start to distribute the energy radially with respect to the direction of flight in the detector. Now, this is not as dramatic as here's, for example, a radio profile for electrons in the H1 calorimeter, and you see it's a log scale, log scale on the y-axis, and a lot of the energy is contained within a cylinder of a few centimeters, which in the central region of the Atlas detector, for example, is very sufficient to separate particle showers. But the more forward you go, and when rapidity collapses on you in linear space, the closer these things get together, and radios like this can become a problem to separate individual particles or create a good image, a good proxy for the flow from individual particles. So I wanted to go to this little game here too, just to show you what's the challenges for the calorimeters. So let's assume you have a particle that has less than 500 MeV. You basically see nothing in the calorimeter, as I said. But if you raise the energy, you start to see things. But the projection, we put a lot of effort in building our calorimeters in a projective way, because we expect the particles to come along in azimuth and rapidity, come along a line. But of course, that's not quite true. The magnetic field actually does funny things to them. So the energy, whatever energy is reached in the calorimeter, is actually not located very well in terms of rapidity and azimuth grid. And that's part of the problems why we don't see it, because the energy is distributed among many cells that have very, very little energy. We just can't see those. But the higher you get in terms of PT, the more you see, and the closer you get to have a full, or at least very close to full absorption of the particle energy. And if this would be a lecture with homework, I would ask you if the formula for the energy is correct for a calorimeter for all particles, but I won't. So I may mention it later. So theory requirements and experimental requirements. And I didn't mention many experimental requirements yesterday because I wanted to kind of show first what the detector does, and then see if we can reflect the requirements on what the detector does to our particles and our jets. So in general, I think we all understand that the detector response and acceptance, so the ability of the detector to see something or not, and the response of the detector should have the tiniest contribution to the kinematics of the reconstructed jet. This is after I fully calibrated it. We try to realize this by calibrating our jets such that they have a linear response in PT, and they have a uniform directional response. That means wherever the jet goes in terms of rapidity, it's measured correctly. This is absolutely non-trivial. As you know, there's transition regions in the Atlas calorimetry, which between the barrel and the end caps, and then inside the end caps, and at rapidity 0, there's literally a crack in the barrel. So there's a lot of problematic regions, and we need to develop a lot of corrections, which we will talk about next week. Clearly, detectors must have sufficient spatial and energy resolution. So meaningful jet definition without compromising infrared safety and collinear stability. There's another interesting question I actually calculated some time ago, and I forgot to put this little drawing in here. I will put it in before I put the transparencies on the agenda. You can actually calculate that if you have a granularity of 0.1, and let's put aside the radial shower effects for a moment, the intrinsic infrared unsafe scale is 50 MeV. So it's very small compared to scales, KT scales, usually live in at the LHC. So that's a good news, and it's also a good guidance for future detectors not to make the calorimeter cells much bigger than what we have. All detectors introduce a threshold because all detectors have limitations. The calorimeter's biggest limitation is noise. You cannot reliably read signals when they're too small compared to the noise in the detector, which can come from the readout system that is usually well controlled. We put a lot of it in the right. But there's also the noise from pileup, which we will have to talk about tomorrow a little bit. But all these biases, thresholds, and intrinsic infrared unsafety must be small compared to what's going on in the particle flow inside a jet. And I think we are quite close to that being true in Atlas and also in CMS. So we really have a good detector to measure jets. The other thing is whatever fluctuations of the signal, they need to be controllable. Again, it reflects how you handle noise and how you remove unwanted, highly fluctuating contributions to your jet. All this we will have to come back starting tomorrow, and then when we talk about jet calibration. This is a kind of a new page. If you, as you all know, we really do like to do jet mass measurements, and we like to do a substructure analysis. So the internal structure of the jet, there must be the calorimeter must generate some image of this flow structure to allow us to do these kind of analysis. The most challenging in terms of calorimeter in the presence of pileup is actually a jet mass measurement. It's highly non-trivial because even the smallest energy deposit from pileup far away from the jet axis deteriorates the mass resolution and measurement quite a bit. So we have to do something about it, and in the future lessons for our lectures, we will see what we can do about it. So these are things you have to keep in mind when you build your detector. You don't have to anymore, we did it already. But let's summarize some partly mentioned some of those. But if you remember our collision diagram or schematics, where we went from the hard interaction through the parton shower, through fragmentation, to hadronization, then at this level already in nature now, whatever tracks come out of this process, there will be tracks added from the underlying event, which we have to think a little bit about. And we have whatever comes from the in-time pileup, so the pileup that is happening, the other collisions that are happening at the same time when I want to read my event of interest. my collision of interest. So, and in addition, you of course have, if you want to define a jet at that level, you have jet reconstruction algorithmic efficiency limitations that you should be aware of. And those can be studied at the level of Monte Carlos. But just to let you know, in Atlas, usually, for example, tracks from PILAB are not in the particle spectrum that is generated by our Monte Carlos. So PILAB is added at the detector level. So the particle jets we can reconstruct from the generated event in Atlas are really clean signal particles, but they suffer from jet reconstruction algorithmic inefficiencies. Anyways, these particles bring us then to what happens in the calorimeter, and that's of course a lot. So we have a whole list of detector effects that we have to take care of. Some of them are design issues, longitudinal energy leakage, for example. Maybe we built our detector not deep enough. Signal efficiencies are usually aging or any kind of readout problems, high voltage problems, things like that. PILAB noise from the PILAB is of course something that is unpleasant in that it increases with time. The more intensity we get at the LHC, the higher this noise becomes, and we have to adjust our strategies to suppress as much as possible this noise. Electronic noise is fairly stable. It's in the presence of PILAB, it has no effect. Our readout is very precise, very little fluctuations in terms of the hardware, but the PILAB is dominating everything. An important thing is how you actually define the signal you want to get out of your calorimeter. We will come to this a little later. Then you have dead material losses, of course, as I mentioned, then the response characteristics, the non-compensating features of the calorimeter. Also in the detector, we have jet reconstruction algorithmic inefficiencies. We lose soft tracks. There's tracking efficiency in general that we need to take into account, because we often combine tracks with jets, or we use particle flow objects right away, which are the combination of calorimeter signals and tracks. Jet vertical association is an important tool that needs to be efficient. We have that is related to tracking efficiency and the ability to reconstruct the tracks pointing to a jet. And of course, everything is challenged in Atlas, at least for the next run, by the restricted tracking detector coverage, which only goes up to rapidities of 2.5, so absolute rapidity. So outside of that, we have to get really creative. So let me reflect, as I think this is the last one I want to show today, and I will definitely come back to this one because it's kind of, it sends an important message, I think. So what we do here is we compare, we have a 4-jet event, 14 TeV 4-jet event. Long before there was any official simulation in Atlas, we did this basically as a private endeavor. And what is called here the hadron jets, that is the way we used to call particle jets those days. This is basically the energy flow from particles collected into small bins in the rapidity azimuth plane. So these are the things you really would like to see exactly the way you see them in this left diagram. So one of the ways of collecting signals are our famous towers. It was actually, and when we wrote this paper, was still quite standard. And you see they do something to the jets already, especially in the central region. They don't look all that great. This is mostly due to the very inclusive signal collection that was applied for this particular version of our towers. But you also see that the forward-going jet, the red jet, is actually not badly resolved in the space, even though the detector that sits there and from which the signals have been collected is non-projective, It's the forward calorimeter in Atlas, which has huge calorimeter cells. But it shows that by projecting the energy in these cells into the tower grid, you can actually recover some of the structures, not in great detail, but at least you see some structure at all. So if you then go to the topo clusters, our famous calorimeter signal, which will have to talk about much more at another time, you see that in the central region, it does quite well in terms of giving the jet structure back, and even the blue jet, which goes in the towards rapidities of 2, is still quite well measured. But then in the forward region, it fails. I mean, it still gives us a jet, but the jet has only 2 clusters in it or something like this. So it's a very small jet. And instead of the 10, 20, or 30 particles it should have. So the signal definition of the calorimeter has an enormous, significant effect on which of the jet you get in the experiment and what you can do with it. So this is something I think I want to send you home with. We will have to come back to this when we talk about topo clusters and other signal definitions in Atlas next week. I think this is all for today. As usually, it's probably a little fast, but you will have the slides, go through them, and you can always contact me afterwards with specific questions. And of course, I'm also happy to hear questions now.
All right, hello, do you hear me?
Yeah.
Yes, a quick question. So on slide 9, you said in quite details that electrons and hadrons would not produce the same signal, but do a pion, a kaon, and a proton of the same energy, or any hadron actually, produce the same signal?
No. There's a difference, and actually, I think when I discuss the Groome's formula, there's 2 base energies given, one for pions and one for protons. They have, first of all, they have a different cross-section when they hit a nucleus. And second, the proton is highly ionizing when it enters matter and generates much more signal than a pion typically. So they are not the same, but they're indistinguishable in jets for us. So we consider everything hadronic that is not a photon or an electron. And we will discuss when we talk about cluster calibration, we will discuss how we try to have a dynamic calibration being sensitive to energy densities and things like that to mitigate the effect of different hadrons. Also, the kaon has normally not the same response as a pion. It's close. The mass is much closer to the pion mass, so but it's not the same. If you do a single beam high precision calorimetry experiment, you see a difference.
Okay. And what about the protons and neutrons?
Well, yeah, the same is true for the protons. Actually, there's an interesting little thing that people tend to forget. If you so the proton again will create a larger signal than a pion, very likely. It will also penetrate deeper than a pion. The interesting case is actually the antiproton, because the measurable energy of the proton is only its kinetic energy. The proton mass will be added to the calorimeter at some point. It just stops and will be absorbed. But if you have an antiproton, it takes the proton out of the calorimeter and generates energy through annihilation. So you have actually a much higher measurable energy for antiprotons than for protons. And there's actually, even in Atlas, there's experimental proof of this. We wrote a paper on the single hadron or single track response a few years ago, where we tagged antiprotons in the track from an antiproton, and we looked at the response in the calorimeter, and indeed it's higher than for the proton tagged tracks. So it's a true effect. But again, in the context of the jet, we cannot separate these things. So we develop the dynamic calibration to take care of these differences as much as possible.
Okay, thanks.
Okay, if we don't have any more questions, so tomorrow we're going to talk about underlying event, what it means for us in terms of jet reconstruction and pileup, which will be we are moving very close to the detector, especially with the discussion of pileup. It's really very different for Atlas and CMS, so I will tell you the Atlas side of things. And then we have a little break, and then we come back to the inputs and calibrations of the jet next week. So if there are no more questions, thank you very much for listening. I will post the slides as usual a little later today. I want to go through them one more time, making sure that not too much nonsense in there. And then there's also a lot of extra material in the slides about calorimetry and other things I hope that are hopefully interesting. So okay.
Thanks a lot, Peter.
Okay. Talk to you tomorrow. Bye then.